Today, we want to remind ourselves that radicals are exponents, get a little review of the notation, and think about some other things that we can do when we're treating radicals as exponents with regards to simplifying radical expressions. So remember that the thing that I want you to walk away from this with, that was a terrible sentence. The thing that I want you to have is that the index of the radical is the denominator of the exponent. The index of the radical is the denominator of the exponent. The index of the radical is the denominator of the exponent. I also want to make sure that we have our pronunciation guide. When we see this expression, we say the nth root of x. We have special words like square root and cube root, but after that, it's just the ordinal, the root of x. So square root, cube root, fourth root, fifth root, sixth root, seventh root, and so on. The way we can pronounce that, the way we could write that in exponential notation is x to the 1 over n, because the index of the radical is the denominator of the exponent. So we would read this expression, we would just say this as x to the 1 over n. The thing that's implied when we say it this way is that the 1 over n is in parentheses, even though we don't speak the 1 over n parentheses. It would be really weird to say x to the 1 over n and mean x to the first power over n. That would be really weird, even though order of operation says x to the 1 over n means this. That's not what we mean when we say this. We mean x to the 1 over n, with the 1 over n in parentheses. So we don't follow the order of operations in our speech. This is one of the things that makes math more difficult to learn. And I did point out that our fractions keep your fractions in parentheses. It helps with the written communication. We don't put parentheses around the 1 over n when we're writing it as a superscript, because the superscript is acting as a grouping symbol. Just like the radical is acting as a grouping symbol, the horizontal bar of the radical acts as a grouping symbol, the superscript is also acting as a grouping symbol. So the radical is a grouping symbol. Also, the superscript is a grouping symbol. Parentheses are not the only grouping symbol. It really shouldn't be PEMDAS for parentheses. It should be GEMDAS for grouping symbols, or GREMDAS, which is, I think, a name I'm going to use for an orc NPC in my D&D game, GREMDAS. All right. So yesterday I posed a fun question where we're thinking about the denominator as an exponent, and it looked like this. We had the fourth root of x to the second. Now, I wanted you to simplify this expression, but there's not enough x's in the radical to simplify, because the 2 is smaller than 4. But if we look at this in terms of fraction exponents, if we remember that the index is the denominator of the exponent, this is x to the 2 over 4. And 2 over 4 we can simplify as x to the 1/2. 2/4 is equal to 1/2. And so we can write this expression, the 4th root of x squared is this just the square root of x. So the radical can change its form if we can simplify. Sometimes we can't. If we had, say, the 4th root of x to the 3rd, that's x to the 3/4, and that's just kind of it. We can't simplify the 4th root of x to the 3rd. Any questions? All right. So let's take a look at one of the things that I wanted to talk about today, and it has to do with this index of the radical is the denominator of the exponent. I really want to emphasize index of the radical is the denominator of the exponent. So what I wanted to look at today was based on this x to the 2/4 is an x to the 1/2 thing. And I wanted to emphasize counting by fractions. So if I have a 4th, and what we want to do is look at the comparison between counting in radicals and how that looks in our fraction exponents. I want to do a side-by-side comparison. So I'm going to start with a 4th root of x. And we know that that's an x to the 1/4 power. And then then let's look at the 4th root of x squared. I'm just going to keep counting up the power of x. This is going to be an x to the 2/4, otherwise known as an x to the 1/2. Because we can simplify that one, which means we can simplify the 4th root of x squared. We could write that as the square root of x. Now I'm going to go up one further. And if I write the 4th root of x to the 3rd, that's going to be x to the 3/4. I'm just counting up the exponents. I'm just counting up the exponent. When I count up the exponent here, 1, 2, and 3, it's all under a 4th root. And so I'm counting by 1/4 powers. If I have a 4th root of x to the 4, that's the same as x to the 4 over 4, which is an x to the 1. So I could write this as just plain old x. Or I could write it as the square root of x squared, which is x to the 1st. Just divide. 4 divided by 4 is 1. 2 divided by 2 is 1. Because the index of the radical is the denominator of the exponent. Now, if I go past 4, I'm going to have a fraction that's bigger than 1. If I have the 4th root of x to the 5th, that's x to the 5/4. And 5/4 can be written as 1 and 1/4. So I want to look at 5/4 is 1 and 1/4. So what we have is an x to the 1 and an x to the 1/4. This would not be how we'd want to write it. We would just leave it as x to the 5/4. But an x to the 1 is just an x. And then this would be a 4th root of x. So when I get to x to the 5/4, 4 of the x's can be one inside the radical, is 4/4 of an x to the 4/4, which is an x to the 1st. And then I have a 4th root of x left over. That's 5. So we're counting 1/4, 2/4, 3/4, 4/4, 5/4. 5/4 is 1 1/4. I actually wanted this down here. 5/4 is 1 1/4. 1 is the complete x, and then the 1/4 is a 4th root of x. Hopefully I'm being suitably predictable. And the next thing is going to be a 4th root of x to the 6th. It's going to be an x to the 6/4. We can simplify that as an x to the 1st and an x to the 2/4. So 4 of the x's is 1 whole x. And then there's a 4th root of x squared left over. So there's 1 left over, there's 2 left over. You can guess what's going to happen next. This looks like an exclamation point, but it's supposed to be x to the 1st times. We can also write this as x times the square root of x, because I have a 4th root of x squared. Because as we're counting up, 1/4, 2/4 is a half, 3/4, 4/4 is 1, 5/4, 6/4 is x to the 3 halves. 6/4 is 3 halves. So if we look over here, we're counting by halves. 1 half, 2 halves, 3 halves. 1 half, 2 halves, 3 halves. Fourth root of x to the 7th is x to the 7/4. I can still only subtract 4 from 7 one time. And then I'll have 3/4 left over. Here are the leftovers. 1/4, 2/4, x, and a 4th root of x to the 3rd. We can think of counting by fractions. And then the last one, since I'm out of space, is where I wanted to end anyway. 4th root of x to the 8th is an x to the 8/4. 8 divided by 4 is 2. So I'd write this as x squared. I can also, since it's 8 divided by 4, 8 divided by 4 can have a denominator of 2. I can write this as 4/2 to get to the x squared. So I could think of this as the square root of x to the 4th. So in fourths, we're counting 1/4, 2/4, 3/4, 4/4, 5/4, which is 1 1/4, 6/4, which is 1 2/4, or 1 1/2, 7/4, which is 1 3/4, 8/4, which is 2. And then it would just go on from there. So counting the simplified radicals, I have a 4th root of x, a 4th root of x squared, a 4th root of x cubed, a 4th root of x to the 4th. Then I have a 4th root of x times a 4th root of x times a 4th root of x squared, x times a 4th root of x cubed, x squared. And so we're just counting with fractions. I think counting everybody is okay with. The with fractions part, we usually don't like. Any questions? So I guess that's kind of the thing that I want to start incorporating. And that's what makes this a good Tuesday topic. We might have bad feelings about fractions, and I'm not really concerned. I'm not going to try to decide for you that you have to like a thing. So you don't have to be all liking fractions. I need the outcome to be that you can deal with fractions and that you can count with fractions. And so this is why I want you to be able to count with fractions, because I want you to be able to look at radicals and see the fractions in the radical. 7/4, 6/4, 5/4, 4/4, 3/4, 2/4, 1/4. I want you to be able to see those fractions in the radical
so that you know you're just counting with fractions. So let's look at another counting with fractions exercise. Let's pull out just the counting with fractions. So, oh, there. I wasn't writing secret stuff. I want you to know we are counting with fractions. Let's count by thirds. So we start off at 0, and then 1/3, and then 2/3, and then 3/3, which is not how we write that. 3/3 is equal to 1. After this is going to be 4/3, then 5/3, and then 6/3, but that's not how we say 6. Oops, I spelled 3 wrong. Here, fixed it. 6/3 is what we normally call 2. And then 7/3, and then 8/3, and then 9/3. Now let's go one more, 10/3. 9/3 we normally call 3. Now in the middle, we have 0, 1/3, 2/3, 3/3, but counting in mixed numbers, 4/3 is 1 and 1/3. 5/3 is 1 and 2/3. 6/3 is 1 and 3/3. 7/3 is 2 and 1/3. 8/3 is 2 and 2/3. But we can also think of 2 and 1/3 as 1 and 4/3, and 2 and 2/3 as 1 and 6/3. Oops, 3, 4, 5/3. I was looking at the 3 when I wrote that. So, and then 3 is 1 and 7/3, or sorry, 1 and 6/3. Once again, I was looking at the next one. I wasn't listening to Yoda. Concerned with where he is, what he's doing. 10/3 is 3 and 1/3, or 1 and 7/3. Now we're getting into weird numbers, like we talked about when we were first starting learning addition and place value. 23 is not just 23, 20 and 3. We can also think of it as 30 and -7, or 10 and 13. But we're listing things really weird. You're like a leech, why are you doing this to us? Once we get to 3, we could say, what if 3 is 2 and 3/3? Then 10/3, or 3 1/3, or 1 and 7/3 is 2 and 4/3. And the numbers start getting weird. But we need to look at these numbers because we need to understand how these numbers are built. When we look at 2 and 4/3, we look at this 4/3 and say, oh, I could have taken another 3 and made a whole out of this 4/3. So I'm going to take 3 more thirds and just put them in the whole number category. Let's think about what we get from 10/3. Let's grab that 10/3. And let's talk about using division to write 10/3 as a mixed number. Let's use division to write 10/3 as a mixed number. We know what the process is. We know that 3 goes into 10 3 times. And the phrase that we use when we say this, the common phrase, is 3 goes into 10 3 times. I don't know what the words you use would be. Do you have different words for saying this? When you say 10 divided by 3, when you come up with this 3, what are the words? I want you to think about what the words are that make you come up with 3. In my mind, I say 3 goes into 10. Sorry. No, I did that right. Amazing. In my mind, I say, I was programmed with this as a child. That's why it's still stuck with me today. I say 3 goes into 10 3 times. That's the words that I use. I'm thinking 3 goes into 10 3 times. And so that second 3 is the one that I put up there. 3 goes into 10 3 times. What it took me a long time to realize is what that means. What I mean when I think that, when I think to myself, 3 goes into 10 3 times, I'm thinking to myself, I can subtract 3 from 10 3 times without going negative. That's what's happening in my mind. But I've always summarized it in this way. But it took me a long time to put it into words. So what this means, I can subtract 3 from 10 3 times before I go negative, without going negative. Y'all are younger than me, so maybe this was explained to you. But one of the reasons that you won't get along with your teachers is that your teachers, it was not explained to them this way. People my age did not get to learn that 3 goes into 10 3 times through various means. I think it was like 9 is the biggest multiple of 3. That's less than 10. But it was never made clear that if multiplication is repeated addition, then division should be repeated subtraction. I was never given that structure. And when I was taught this as a kid, probably that would have been too far along. But in algebra, no one ever told me that multiplication is repeated addition, so division should be repeated subtraction. And this 3 means the number of times I can subtract 3 from the 10 without going negative. And then what we do is you do 3 times 3. So I'm just going to follow my process. 3 times 3 is 9. Here I am subtracting the 3 3s from the 10. And there's 1 left over. So that's literally what's happening here. Here we are. Here we are. Back in the car again. Mostly because I was programmed with this process. It wasn't explained to me. I wasn't required to understand what the heck was going on. I was just told to do this. And I saw whenever any of my fellow students said, but why? They were told, be quiet and just do the thing. And only the best students among us rebelled against that and got sent to detention. And then so there's 1 left over. After we subtract 3 from 10 3 times, there's 1 left over. So we can subtract 3 from 10 3 times, and there will be 1 left over. And that's what this quotient means. We can subtract 3 from 10 3 times, 3 from 10 3 times with 1 left over. What I wasn't told was that you can't get this wrong. That's just it. I was not told that you can't mess this up. So what if we do, it's fine. Nope, this one. Let's suppose that we're like, oh, 3 goes into 10. Let's suppose we don't notice that it's 3 times. Let's suppose that we, quote, mess up. I know I can subtract 3 from 10 twice. These numbers are very small to make things work. But what if we get it wrong? What if we just don't recognize that you could subtract another 3? So I'm going to subtract 3 from 10 twice. So 2 times 3 is 6. 10 minus 6 is 4. Look, I could have subtracted another 3. So because there's 4, it's like, oh, look, I can subtract another 3. So I will just change this to a 3, and I'll subtract another 3, and there's 1 left over. Now we're done subtracting 3's. Now if we subtract another 3, we're going to go negative. So it's 3 1/3. Same result. Here, we were being overly cautious. We only took off 2 3's. What if we're overly aggressive? What if we're overly aggressive? Then what we'll have is, let's say you subtract 4. It's like, well, how many 3's do you want to subtract from 10? You're like, oh, 4. Go big or go home. 4 times 3 is 12, and 10 minus 12 is negative 2. Whoops, we've gone too far. But one thing we want to notice is that even though this is not how we would write these numbers, 2 4/3 means 3 1/3. 2 4/3 is the same as 3 1/3. Moreover, 4 and negative 2/3 is 3 1/3, because if you take 4 and subtract 2/3, where are you at? 3 1/3. You can't mess it up if you understand what's going on. 4 and negative 2/3 is equal to 3 1/3. Because the other thing that we have to remember about fractions is that 3 1/3 means 3 literally and 1/3. So if we have a negative remainder, that just means we're subtracting. So rather than being given the, I don't know what your fraction education was like, but I know for my fraction education, I was told we had to get it right here. We had to get that 3 correct. If you put a 2, it was wrong. We weren't taught how we can get our way out of it. We weren't taught how to fix it. We weren't taught that 2 4/3 is not how we write things, but it means the same thing as 3 1/3. We weren't taught that if we can subtract 12 from 10. First of all, that's the other thing that we're always told in school. It's like, oh, we can't take 12 from 10. And then most students that are going into debt for things know it's like, oh, you can absolutely take 12 from 10. I got $10 left, and I have to pay a bill that's going to be $12. They're going to get it. I have negative $2. So rather than being given the opportunity to explore things and learn how things are put together, we're told it has to be this way. That's what's wrong. That's what modern math teaching is trying to correct. Because it's trying to emphasize understanding and how things work rather than do this thing this one way. Oh, I'm pointing at the wrong one. Do this thing this way. This is the only way. It's not the Mandalorian up in here. There are other ways to get where you need to go. But you do have to recognize that when instead of saying 2 4/3, just say, oh, wait, no, 3 1/3 is what I meant. That's how we normally say these things. You know what I mean? We're counting with fractions because the index of the radical is the denominator of the exponents. We're just counting with fractions. I want to make sure that we have a better understanding of how fractions should work. Any questions? All right, that's it for today. I will see you all on tomorrow, but not on Thursday. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.